That's what we named it. You want me to do this one?
Yeah, do that side.
Okay, so our location, we chose a crater called Hellas Planitia. It's located in the southern hemisphere, and it's the third largest crater on Mars. It is roughly 1,400 miles in diameter and 23,000 feet deep. And then we have a little video to go along with
Why did
this.
you pick such a big crater? That's so big, so the wind doesn't get you?
They're going to talk about it later in the
Oh, sorry,
presentation.
sorry.
It's all good.
Okay.
That's good that you're asking questions.
Yes. Okay, you said like 153, right?
153, I think, yep.
That's like halfway.
Yeah.
It's 43, keep going. I'm trying. Good enough. Okay.
Hellas is an ancient impact structure and is the deepest and broadest enclosed basin on Mars. It measures about 2,300 kilometers across, and the floor of the basin, Hellas Planitia, contains the lowest elevations on Mars. The Hellas region can often be difficult to view from orbit due to seasonal frost, water ice clouds, and dust storms. Yet this region is intriguing because of its diverse and oftentimes bizarre landforms. This image from eastern Hellas Planitia shows some of the unusual features on the basin floor. These relatively flat-lying cells appear to have concentric layers or bands, similar to a honeycomb. This honeycomb terrain exists elsewhere in Hellas, but the geologic process responsible for creating these features remains unresolved.
Yeah, it's really cool.
That's enough.
Okay.
Sand dunes are scattered across Mars,
Okay.
and one of the larger populations exhibit
Okay. Alrighty.
Okay, Earth versus Mars. The gravity on Earth is 9.8 ms.
Meters per second squared.
Yes. It's squared.
Meters, it's supposed to be meters per second squared. Don't worry about it.
Okay.
F equals MA.
Mars is 38% of Earth.
So it's like 1/3.
The air pressure on Earth is 4.7 psi, and on Mars it is 0.088 psi.
And PSI is pounds per square inch.
So it's like 1/100th.
Yes.
That's gonna be a problem.
The
I hope
temperature
your kids have-
average for Earth is 58 degrees Fahrenheit. On Mars, it's a range of -81 degrees Fahrenheit to 68 degrees Fahrenheit. One day on Earth is 24 hours, and 1 year on Earth is 365 days. As for Mars, it is 24 hours and 40 minutes for 1 day, and there are 687 days. Earth's sunlight is 683 WM squared,
Watts per meter squared.
and Mars is 300 WM squared, which is 44% of Earth.
Yes.
So, psychologically, Mars colonists are gonna be appreciative of this day length.
Yes, because it's nearly the same as Earth's.
So sun rises, sunsets, sun rises,
Yep.
sunset. All right, and that difference in sunlight is just because Mars is that much farther away from the sun?
Yep.
Okay.
My stuff. Okay, so the base, alright, so the base can be mostly underground, built into the side of the crater, and that's just for a lot of protection benefits. So I kind of drew out a basic idea. It'll be constructed a lot from silver and gold, and then carbon nanotube plastic, and then padded silicon for certain comfort items. And of course, it'll all be printed from a 3D printer, because that's easier than hauling a lot of these materials, which a lot of this will be found from meteorites scattered on the surface. And then there is lead that can be used for a radiation shield against a lot of the sun's evil radiation. Then the dome for our entrance point on the surface, that'll be constructed from plexiglass bicarbonate, and then of course it'll be state-of-the-art facilities. So this is kind of the supply pad, and then a bird's eye view into the crater where we'll have possible future livestock and a greenhouse, and then a utility dome for water and sewage and our electrical systems throughout the base. Alright, so this video is of a moon colony, but a lot of this is applicable to Mars, so this could be what happens on the surface.
Planet Earth is protected by the atmosphere, the layer of air and gas that surrounds it. The atmosphere shields the Earth from solar radiation, keeps the temperature balanced, and protects us from meteoroids. On the Moon's south pole, you can see almost perpetual sunlight on the horizon. This is the site of our lunar base. Conditions on the Moon are very different from those on Earth. Because the Moon has no atmosphere, there is no protection from solar radiation. There are extreme temperature fluctuations,
Can you pause it?
and there is no protection from gamma radiation.
So, Moon and the Earth, same distance from the Sun. The temperature range on the Moon is, I think it's like 500 degrees, the range from the coldest to the warmest, compared with the range on Earth, which at the worst, it's 100 below, and at the worst, it's 100 above. So we have maybe a 200 degree temperature difference. And so that idea that we have these greenhouse gases in our atmosphere is so huge. So again, this is a moon colony that we're looking at here, but Mars is going to have similar challenges as far as temperature goes. And protection from micrometeorites and stuff, so anyway, sorry.
And no protection from meteoroids. The lunar lander has detached from the rocket launch and is on a course to Shackleton's crater, the Moon's south pole. Inside the lander is a cylinder which contains an inflatable dome and 2 robot 3D printers. After the cylinder containing the habitation capsule has been unloaded, a dome is inflated from one end. This provides the support structure for construction, a little like scaffolding is used to build on Earth. The lunar habitation is built by a robot-operated 3D printer. At one end, it has a scoop to collect the regolith. In the centre are the containers for the printing material. At the other end, there is a robotic arm with a printing head. The robot collects regolith from the Moon's surface. Layers of this moon dust are built up over the dome to create the protective shell. This process takes about 3 Earth months. The shell is made up of a hollow, closed cellular structure. Under a microscope, it would look very similar to the close-up of a bird's bone. Like a bone, it is light and incredibly strong at the same time. When the lunar base is complete, it can house 4 people. Inside the dome, they are protected from meteorites, gamma radiation, and high temperature fluctuations. The original capsule functions as an airlock and technical support module. The skylights draw daylight into the living and workspaces, which are sheltered within a pressurized enclosure. This method is a pioneering advance in space-age construction. At Foster & Partners, we're used to designing for some of the world's most extreme climates. We often use materials found locally to create sustainable buildings on Earth. While the Moon is an exciting new territory for architecture, the value of this logic endures.
So that's kind of how they would do the main supply dome. And this is digitally concepted ideas of what the base could look like. So this could be the supply dome, and then you've got your possible idea of the greenhouse, as you get more space growing vertically than you do on the ground. And then a bedroom, and then possible living, common space, and for all the astronauts. So this could be where a lot of their equipment is stored, which is very beneficial to their health.
Alright, I'm doing electricity for the most main part of our project. Starting off with solar radiation, or solar energy, which we can use these to collect energy from the sun, since a Mars day is the same as an Earth day. It gets the same amount of sunlight, and you can collect a lot with these. Next is wind power. Since Mars has wind on it, or low wind, it will use these two to collect energy from the wind whenever wind does happen on Mars. Hydroelectricity. Since Mars has an icy core, we can take the water and melt it and bring it through turbines to make energy through generators, which is another easy way to do it. And then through all of these, we could have batteries on them, since batteries are really good at storing energy. Each one can have a battery, and rovers can go out and collect them and store up all the energy from every single one of them.
So, Sammy and I had electricity, but unfortunately or not electricity, atmosphere, but unfortunately she couldn't make it today because of IMC, so I would be doing it for both of us. So, pressure would be the hardest to obtain, because if we don't get the right pressure, we wouldn't be able to breathe with the right pressure. We have a little demonstration here in a little bit. With the greenhouse gases that are already on Mars, we could capture that and collect the nitrogen from bacteria that's on Mars to help sort of have a gas that isn't reactive, like Ward said, to help sort of keep the gases together. We can decompose carbon dioxide that we exhale from breathing and water, H2O, to make methane for fuel and heating for the base. And we can release it back into the base's atmosphere through vents and stuff like that to create a more friendly atmosphere for us. There we go. And so air control. We'll use vents and air conditionings to capture the carbon dioxide that we exhale and then give it to the base's greenhouse, and we can also use the carbon dioxide, like I explained earlier, to make methane for heating and fuel. Oxygen also releases from plants that we can capture and use for breathing and releasing it. We can also use some amount of water to be used to decompose to methane, and then a short little video for the presentation.
Oh, is this Moxie? This is so cool.
We've all seen The Martian, and we know we need breathable oxygen to survive on Mars. What's up, Watney? It turns out it's a lot better to be able to extract it from the atmosphere of Mars, then bring it with you on the trip over, if you have the technology. Let's see how close we are on this episode of Crazy Engineering. I'm here with Jim. He's going to teach us how to get oxygen on the surface of Mars. Jim, can you tell us where we are right now?
Absolutely. This is the JPL Mars Oxygen In Situ Resource Utilization